Hello everyone, my name is Garima and today we will discuss the design of the CPU and how this has been translated to HDL code. So let's start with our presentation. First, we will have a quick recap on Hack Computer architecture. Hack Computer consists of a CPU and two separate memory modules, which is instruction memory and data memory, and two memory mapped I/O devices also, which is screen and keyboard. Hack CPU consists of an ALU which is capable of performing 18 different arithmetic and logical operations depending upon the 6 control inputs. The CPU also contains three 16-bit registers, which are D register, A register, and the PC. D register is used to store data values. A register have three different purposes, which is used to store data values. It also points to the address inside the data memory. It also points to an address inside instruction memory. Then we have program counter. So the PC points to the next instruction that has to be executed. Now we will have a look on input and output pins of the CPU. So the CPU contains three input pins, which is INAM, the instruction, and reset. In INAM is a 16-bit value which comes from the data memory, and this is the value at which the CPU is going to operate on. Next is instruction memory. It's a 16-bit value named instruction. This is the value which instructs the CPU what operation to perform. Then we have our reset. It's a single bit value and is a restarting signal. Then we have four outputs, and the first three outputs deal with the result of the computation that needs to be written somewhere in the data memory. So first one is outem, and it's a 16-bit value. It contains the result generated by the ALU in a value. Then we have a single bit load pin named writeam, which enables to write in the data memory. Then we have address M, a 15-bit address to the data memory. Then we have PC, which is the fourth output. This contains the address of the next instruction, which needs to be fetched and executed in the next cycle. So now we will talk about the reset pin and the PC in more detail. So if reset pin is set to 1, then the 15-bit output PC emits 0, causing program to restart. So if reset pin is 0, the CPU logic uses the instructions jump bits and the ALU's output to decide if there should be a jump or not. So let's consider this example. This 54 is placed inside the A register, and this computation D-1 would be performed by the ALU. And if it outputs 0, then PC is set to the value of A register, that is, a jump would be performed. And if this condition is false, then the output is PC++, which means by default the next instruction would be followed up. So now let's take a look at the hack CPU implementation diagram. So it's exactly what we saw in previous slides. Here the C symbol represents a control bit. We will study about all these components in detail with the help of HDL code. Here is our full HDL code. I'll explain this entire code in parts as we move further. So it's our first part of the code. We have the header section, which contains the chip name and input-output pins. As we saw in earlier the code contains three input pins and four output pins, which we studied earlier. So we should move on to the next part. Here is the first part of parts section of cpu.htl code. So we have four gates here which allow the CPU to perform certain functions. In first line of code, NOT gate is used, which determines whether the instruction is an A instruction. Before that, let's take a look at this diagram above. So in this, the instruction coming from the data memory is decoded first by the CPU into a single bit opcode and a 15-bit value. If the opcode is 0, then the next instruction is A instruction, and if the opcode is 1, then instruction is C instruction. So if our instruction is A instruction as determined by the NOT gate, then the CPU takes the specified 15-bit value and stores the value in the A register. And if it's C instruction, then it goes in the ALU where computation is performed and the ALU output is fed to the A register. We use AND gate to determine whether the instruction is a C instruction, and a multiplexer which selects whether the ALU output or the A instruction value should go to the A register. So in the next part we have OR gate. The load pin bit in the A register would be 1 if either the A instruction or ALU output is fed in A register. As we know, A register is used to store the value that is fed in the A register. So A register takes the output A register in from the multiplexer and output load A from the OR gate as its inputs. It has output pin A out, which generates the value inside A register. Then the other multiplexer, it takes the output A out from A register and enum, which is the value that is currently selected in data memory register. It selects whether A or M would be fed in ALU depending upon 12-bit instruction value. And now AND gate. AND gate is used to determine whether the ALU output is loaded into the A register. Sorry, in the D register. And then comes D register. D register is implemented to load and store the value of D register from the ALU. So now our next part contains the ALU. ALU, which does the computation part. It computes a function on two inputs. This can be the value which is stored in the D register, or it can be any value from D, M, or A register and generates the output accordingly. So it consists of the input control bits like ZX, NX, ZY, NY, F, and NO that indicate which function is computed on the inputs of the ALU to perform the desired output. It also contains of the output control bits like ZR and G, which determine the property of the result. Then we have two OR gates and one AND gate to set the ALU outputs in order to write to the data memory. So in this part of cpu.htl code, the load bit of the PC is determined by the jump bits and ALU outputs. These lines of the code determine the jump instructions, check the ALU outputs, and see if the conditions are met or not. So if the instruction is C instruction and the conditions are also met, then the PC is loaded with the value that will ask the CPU to jump to a specified instruction. If PC is not loaded, then by default it jumps to the next instruction like we do PC++. So this is how CPU implementation works. This is how this HTML code works. So thank you so much for listening to me, and like and comment if you liked my video. Thank you so much.